Another important part of a optical instrument is optical filter. Filters are frequently inserted in the optical system to control the distribution of radiant power or wavelength. When the glass is partially silvered, most of the power is reflected and the desired fraction of power is transmitted. When carbon particle are suspended in plastic, most of the power is absorbed and the desired fraction of the power is transmitted. And also, two polarized filter may also be used to attenuate the light. Color filters transmit certain wavelength and reject others. We have um, four well-known color filters: gelatin filters, glass filters, and interference, and also diffraction grating filters. The two first filters are simple in structure. Gelatin filters are the most common type of absorption filters. We can use an organic dye, solve it in an aqueous gelatin solution, and a thin layer, thin film can be dried on a glass substrate. Also, glass filters made by combining additive with the glass, coloring additive with the glass itself in its molten state are extensively used. But these kinds of filters are complex filters. Interference filters are formed by depositing a reflective stack important parts of this filter, some stack of layers on both sides of a thicker spacer layer. These layers reduce heat within the optical system without sacrificing the useful light. And also diffraction gratings are widely employed to produce a wavelength spectrum in a spectrometer, and these plane gratings are formed by cutting thousands of closely spaced parallel grooves in a material. As you can see in this figures, interference filters, we talk about some stacks of layers, and you can see everything is about the wavelength and the thickness of these layers. The thickness of layers is the main um, um, is the main rule, is the main uh, reason for transmit or reject. In other words, reflect. You can see if the wavelength of the signal, if the 0 point, you can see the 0 point of the incident ray are located on the two sides of the layer. The incident ray can pass through this layer, but if the wavelength is larger or smaller than the situation, the wavelength will be reflected or absorbed by the layers. The 0 point of the wave means that if I incident lambda, the proper thickness of layer can be lambda, half of lambda, or quarter of lambda, and uh, so on. It means that um, we should emphasize that a layer with the thickness of half of lambda is suitable for transmitting, and also this layer can transmit some rays with a wavelength of quarter of lambda. The grating filters, as I told you before, we have some holes, some small holes, as you can see here, and it's related to the wavelength also. And this hole, this exact holes, only allow to transmit specific wavelength of the incident ray. Also, we can fabricate some varying filter. With changing these holes, we can build a varying filter. The last part of this lecture is about radiation sensors we use in optical systems. Radiation sensors may be classified into two general categories: thermal sensors and quantum sensors. Based on those names, we can get the main principle of those sensors. We start from thermal sensor. The thermal sensor absorbs radiation and transforms it into heat. Repeat it. The thermal sensor absorbs radiation and transforms it into heat. Therefore, we are talking about heat, not radiation. We should transform the radiation into heat, and after that we can measure the heat related to that radiation power, and based on this temperature we can determine the power of that radiation, thus causing a rise in temperature in this sensor is the main index of the radiation power. Typical power types: the thermistor and thermocouple, and thermistors. The sensitivity of such a sensor does not change with wavelength, and the sensor has a slow response. Maybe we can say the response is flat with wavelength. A wide range of wavelength will affect the response of the sensor, and we cannot use this type of thermal sensors to a specific wavelength. The pyroelectric sensor absorbs radiation and converts it into heat. Rise in temperature changes the polarization of crystals, which produce a current proportional to the rate of change of temperature. As it is for the piezoelectric sensor, DC response is 0, so a chopper is required for DC measurements. But Based on the name, quantum sensors absorb energy from individual photons and use it to release electrons from the sensor material. Typical quantum sensors are our eye, the phototube, the photodiode, and photographic emulsion sensors. Such sensors are sensitive over only a restricted band of wavelength. Most response rapidly. Changes in ambient temperature cause only a second-order change in sensitivity of these sensors. Photoemissive sensors is a quantum sensor. Photoemissive sensor, for example, phototubes, have photocathodes coated with alkali metals. As you can see, if photons have sufficient energy, photocathode can emit electron because inside the photocathode that photon can forces that bind electrons to emit. Photon multiplier, and I add some words at the end of this word, photon multiplier tube, is a phototube combined with an electron multiplier. Read the text first, and after that we will talk about this figure. Each accelerated electron hits the first dynode with enough energy to liberate several electrons by secondary emission. These electrons are accelerated to the second dynode where the process is repeated, and so on. Time response is less than 10 nanoseconds and are the most sensitive photodetector, which we use in some radioactive detector. Okay, let's speak about this figure. This is the schematic of photomultiplier tube. We start from a photon, hits to photocathode. Photocathode is a layer react with photon and also serves as a cathode. Cathode means generates electron. Therefore, we have electron at the outside of the photocathode. We have some electric mirror, we call it diodes, and also some voltage divider here. We have some resistance here, as you can see, some resistance here act as voltage divider. Therefore, if we have a huge electric field, as you can see, 1 kilovolt, this is 0 voltage, and this is a negative 1000 volts, and using 10 resistance, now we have negative 900, negative 800, and so on, negative 100 volts, and also 0. When the electron extracted from the photocathode will be accelerated to reach the first dynode. Dynode first. As a billiard game, if this accelerated electron hits the first dynode, it will extract 2, for example 2, it can be more than 2 electron we assume that only 2 electrons will be extracted by heating the diode. 2 electrons will be extracted from the, or liberated, will be liberated from the first diode. These 2 electrons will heat the second diode and leads to liberate 4 electrons from the second diode, and it will repeat it. This procedure will be repeated, and because of having 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 diodes, we can extract 2 power of 9 electrons because of only 1 photon. This is a good deal. Very good deal. Most sensitive photodetector, we build it with this structure. But you should tell me, what is the source of this large number of electrons? What is the source? What is the origin of these electrons? I answer this question. The source of this large number of electrons is this high electric field. This power supply will be support the extraction of these large number of electrons. And now you can find only 1 electron in the field, in the environment. That's so good. That's amazing. The next sensor is photojunction sensor, are formed from p-n junctions and are usually made of silicon. As you can see, photons, if have sufficient energy, can jump the gap band, generate whole electron pairs, and emits electrons. We use p-n junctions in reverse bias, and therefore the we increase the gap, we increase the linearity with also this situation, this structure, as you can see in the reverse bias, without any radiation, we have a small reverse current, but with 1 millivolt radiation, the inverse current will be increased, and the radiation increase the current, the reverse current, linearly, and that is good for our objective. The response is more than nanoseconds because we need to generate electron holes. And the last sensor is photovoltaic sensors. The same silicon PN junction can be used in the photovoltaic mode and sensors. There is an open circuit voltage. When the junction receives radiation, the voltage rises logarithmically from 100 to 500 millivolt as the input radiation increases by a factor of 10,000. This is the principle of solar cell that is used for direct conversion of the sun's radiation into electric power. Also, in the medical instrumentation, photovoltaic sensors are not a widely used sensor, but this type of sensors is a common radiation sensor in industry devices, industrial devices. Okay, thank you for your attention. This was the last slide of this lecture. Good luck.